Hi everyone, in previous class we are discussed about the electronic configuration, means the electrons are distributed in different orbitals is called as an electronic configuration. So some exceptions are there in an electronic configuration. So what are those exceptions and why those exceptions are happen? We got the answer in today's class. In today's class I wish to discuss with you the stability of half filled and the completely filled subshells. Let me see here, let me write here the electronic configuration in 3D series. So this is our 3D series: scandium, titanium, vanadium, chromium, manganese, ferrous, cobalt, nickel, copper. So these are our 3D series. I wish to write the 3D series configuration here. Scandium 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. So the atomic number of scandium is 21, and next 2 plus 2 4, 4 plus 6 10, 10 plus 2 12, 12 plus 6 18, 18 plus 2 20, 20 plus 1 21. So see here, these are equals to 21 electron. So this is our electronic configuration of a scandium. I write a titanium configuration here: 1s2, 2s2, 2p6, 3s2, 3p6 and 4s2, 3d2, because we are having 22 atomic number for titanium. And next for vanadium, up to this much, this is a same configuration here, just here one electrons comes in this 3d orbital, 3d3 for vanadium. And next, what about in a chromium? So see here, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. So see here, is this a correct configuration for a chromium? No. So this is a wrong configuration for chromium. In a chromium, some exceptions is there. So here what happened? See here, this 4s2 electrons in this subshell, 4s subshell, we are having a 2 electron. So instead of 2, here we have only 1 electron. Instead of here 4, we have 5 electron, 3d5. So this one is a correct configuration for chromium. Why it happened here? Why here we can't write 4s2 and 3d4? Why this is not takes place? Why this is takes place in this electronic configuration? So this is because of the stability of an atom. So what is that stability? I will tell you later. And next, see here in a manganese, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d5. So see here, 25 is the atomic number. Just we have to add these numbers: 2 plus 2 4, 4 plus 6 10, 10 plus 2 12, 12 plus, so this is 6, 12 plus 6 18, 20, 25. And next in a Fe, up to this one same, here I write 3d6. So in a cobalt, 1s2, 2s2, 2p6, 3s2, 3p6, 3s2, 3p6, 3d7. And next, here this is the same, 3d8. Next, what happens in a carbon? So see here, 1s2, 2s2, 2p6, 3s2, 3p6, 3p6, sorry, just I forgot to write the 4s2 here. 4s2, now 3d7. Here also 4s2, 3d8. And next see here 3p6, 4s2, 3d9. So is this happen in a copper? Is this a correct configuration for correct configuration for a copper? No, this is a wrong configuration. So here what happened, instead of 4s2 I write a 4s1. Instead of 3d9 here I write 3d10. So why this exception is also happen in a copper? So in a chromium and in a copper we got a slightly little bit different electronic configuration. So why these exceptions are happen? So see here the stability of an atom. Just I wish to explain about that stability. So see here, as the ground state of electron configuration on the atom is having lowest total energy in a certain element such as a copper and a chromium. So see here, such as a copper and a chromium, where the two subshells 4s and 3d, what happened? Differ slightly in their energies. 4s and 3d are differ slightly in their energies. Then the electron shift from the subshell of lower energy of 4s to subshell of higher energy of 3d and provide the extra stability. So see here what happened, the electron shifts to the d orbital and then that provide the extra stability to this atom. For that extra stability only this exceptions takes place. So as a result of valence electron configuration, so when the 4s electron is shifted to the 3d, then what happens and what results will come? 4s1 and 3d5 instead of 4s2, 3d4. So see here 4s1 to 3d10 instead of 4s2 to 3d9. Instead of we write like this. And next, what facts causes a stability in an atom? There are two facts to cause the stability, like symmetry and exchange energy. So what are you meaning by this symmetry and the exchange energy? Let me tell here. The half filled and completely filled configurations are more symmetrical because of symmetrical distribution of electrons. Means same number of electrons exist in all orbitals. So see here, in a d5 orbitals, I fill the electrons like this. 1, 2, 3, 4, 5. So these are different 5 orientations, d orbitals are there. I fill electrons in all orbitals like in this manner. 1, 2, 3, 4, 5. So these are 5 electrons of d orbitals are similarly or symmetrically distributed in this d orbital. In all orbitals have the same number of electrons in same directions. This is called a symmetrical distribution of an electrons. And I wish to give another example here. 1, 2, 3, 4, 5. So these are again 5 orbitals. I have 10 electrons to fill here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. According to the Hund rule, I fill the electrons here. Then observe here again the symmetrical distribution of electrons takes place here. Because in all orbital we have a same number of electrons. This is called as a symmetrical distribution. This is completely a half filled orbital and this is completely a full filled orbital. So see here, the half filled and completely filled configurations are more symmetrical because of symmetrical distribution of electron, and this symmetry leads to the greater stability. The reason of the symmetrical distribution of electrons takes place here. So this symmetrical distribution of electrons lead to the symmetry, and this symmetry lead to the greater stability. So this is the one reason why the stability cause here. The next point is exchange energy. So what do you mean by the exchange energy? Let me tell here. The stabilizing effect arises whenever two or more electrons with the same spin. Just observe these points. The electrons are with the same spin and are present in a degenerate orbitals. So what do you mean by degenerate orbitals here? So different orbitals are present in the same energy level, called as a degenerate orbitals of a subshell. These electrons tend to exchange their positions. So these electrons tend to exchange their position, and energy released due to this exchange. Due to this exchange, some kind of energy released there. This energy is called as an exchange energy. So let me tell here by the example. We have a 5 degenerate orbitals in a d subshell. These are 5 orbitals, 1, 2, 3, 4 and 5. We have a 5 orbitals with the same spin. So these electrons are exchange their position. So consider this is our first electron, and this electron exchange their position here or here or here and here. So how many exchanges takes place here? 1, 2, 3, 4. 4 exchange takes place by electron 1. And let's see here, these are again 5d orbitals. We are having 5 electrons with the same spin. If the position exchange by second electron, if the position exchange by this electron, then how many exchanges takes place? So these exchanges takes place here. So 3 exchanges takes place by electron 1, by electron 2. Here this electron exchange this position. So by this exchange, some kind of energy released there. So this is called as an exchange energy. So these are the two facts causes of stability here. This exchange energy is maximum in half filled d orbitals or a full filled d orbitals. So in the chromium in the chromium and copper, that kind of exceptions takes place in their electronic configuration.